In the previous video, we talked about conservation of charge, which basically says if nature creates a positive charge, at the same time it creates a balancing negative charge in such a way that the total charge of the creation is equal to 0. We also talked about the force between charges. We talked about Coulomb's law and how that works. We also said that current is the movement of charge. And now I want to present the concept of a force field, what we call in electronics an electric field. Let's say that we have an isolated positive charge. And we bring a very tiny positive charge close to this bigger positive charge. Now we know that like charges repel each other, so there will be a force on this tiny charge away from the big charge. And if we bring this positive charge even closer, we know from Coulomb's law that the force increases. The force is even stronger here. Now we can think of this force field or electric field as rays emanating from this positive charge. And so on and so on. Now notice that as these lines converge at the positive charge, they're closer to each other. And at the same time, the force between the small positive charge and the big charge is more intense. As we come further away from this positive charge, the force becomes less. And if you look at the separation between these force lines, the separation is greater, which means the force is less. So here, where the lines are closer together, the force is greater. Here the force is less. Let's take this positive charge and let's place a negative charge below it here. Now this will distort the force field, or what we call electric field. We'll have a strong field that will push a positive charge here towards a negative charge. And if we draw these force lines, they'll tend to look like this. And out here, the force will be diminished. And out here further, it'll be further diminished. And these lines, force lines, are separated further apart, which is an indication that the force on this tiny charge place here will be less. So let's draw some more field lines. So if we put a positive charge right here, this is the maximum field strength. These lines are the closest together. And this charge will move away from the positive charge towards the negative charge, since opposite charges attract each other and positive charges repel each other. Let's say that we can do some work on charges and we can separate positive charges from negative charges. And we can anchor these charges like we did last example on a metal plate and on a metal plate. Now let's examine the force field between these two plates. Now here we'll have the field will repel. If we place a small positive charge here, this positive charge will be forced in the direction of this arrow towards the negative plate. So let's draw some more field lines. It'll be pretty uniform in here. But once we start getting near the edge, the field is going to diminish. So these lines are a little further apart, which means the force is a little less out here. and so on and so on. This is a little bit analogous to the gravitational force. So we have the Earth here, and we have ground. And we take an object, for example, a rock, and we let go of it. That rock will fall towards the ground because of the gravitational field that the Earth creates. Now this force field, this electrical force, what we call the electric field, is very similar. If we place a positive charge up here, it'll be forced in this direction towards the negative plate, just as this rock falls towards the ground. Now when this positive charge reaches this bottom plate, it's at rest. It can't fall any further. So in electronics, very often we'll call this most negative region, we'll call it ground. Because the charge has come to rest on this negative plate, just as the rock comes to rest on the ground of the Earth. Let me erase this. Let's talk some more about charge and current. Just as the dollar is a unit of money, the coulomb is a unit of charge. Now, how much charge makes a coulomb? It turns out that 1 coulomb is equal to 6.24 times 10 raised to the 18th power electrons. Now I'll put E with a minus because electrons have minus charge. So a coulomb is a lot of electrons. It's like 6 followed by 18 zeros. That is a lot of electrons. But how much really is a coulomb? We know an electron is really a very tiny charge. So how much is a coulomb? Let's say that we could take a copper penny, if you can find a copper penny nowadays, and this is 1 cent, and ask ourselves, if we take all of the electrons in this copper penny, how many coulombs would we get? If I did the calculation right, we would get 130,000 coulombs. Coulombs of charge. This is, if we added up all the electron charge, not counting the positive charge in the copper atoms, just the electrons, we'd have 130,000 coulombs of electrons. Let's say we could take this copper penny and we could turn it into a copper wire. Let's say that, well, we'll have a copper wire here. That's the same diameter as that penny. And let's say that we could put some negative charge at this end of the wire and some positive charge at the other end. And we can create an electric field that is positive to negative. And we know that we have a lot of mobile electrons that are free to move within this copper wire. And let's say that we could take a cross-section of this wire and ask ourselves how many electrons will pass this cross-section and be attracted to the positive charge. So we know that any electron in this copper wire will be attracted towards the positive charge. So let's say that we had 1 coulomb of charge pass this vertical cross-section every second. So if we had 1 coulomb per second coming past this vertical point, then we would call this 1 amp or ampere of current flow. Now if we could make this electric field more intense, put more charge here, we could increase the current flow. We'd have a stronger electric field in this copper wire. These electrons would be propelled at a faster rate towards the positive charge. So the amount of electron flow in this direction would be increased. If we could increase it to 2 coulombs passing this vertical point every second, then we would have, this would equal to 2 amps of current flow.